Look, I'll volunteer. What?
Okay, let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, there is an award that I'd like to present. Each year, the university likes to recognize its long service employees, and we have several in our department. One in particular has been with us for 15 years, and she is our office supervisor, and she's more than just an office supervisor. She helps everybody, especially me. And when she's not here, either out on vacation or out sick, I know it because it makes my job a lot tougher. And so this is the type of person that helps everyone. And so it's always a pleasure to recognize somebody like that. And so the person is, of course, Lydia Salmon, and the university has given her a very nice necklace and bracelet. And so if she'll come forward, and let's give her a round of applause. Yeah. More play. All right. And now for today's speaker, who is Dr. Tony Gabriel. He is a senior team leader for target systems for the Spallation Neutron source at the Oak Ridge National Laboratory. Tony is a longtime friend of mine. We have known each other for 35 plus years, longer than some of you have been living. And in fact, we worked in the same division together for several years. And Tony is a very interesting person. He's a very good friend of this university. He received his PhD in physics in 1969 and went to work for R&L. And he has risen through the ranks at R&L, becoming a corporate fellow. He's also a fellow of the American Physical Society. He teaches scuba diving, or at least he used to when he was a little bit younger. I almost took a course from him. Then I figured out that I could swim better than he could, and so I said, I don't want this guy teaching me to do scuba diving. So the subject of his presentation today is overview of the Spallation Neutron source with emphasis on the target systems, which is his responsibility, the target systems. So ladies and gentlemen, please welcome my friend, Dr. Tony Gabriel.
It's always a pleasure to come back to the University of Tennessee, and I'm very glad that Dr. Dodds, I shouldn't be so formal, that Lee has invited me back, since he and I have a long-time relationship. By the way, some of you graduate students, I've got a black book with a few things. If you need a few in yours, just come see me. It is a pleasure to talk about the Spallation Neutron source, and also I'll be giving an emphasis on the target systems part, since it is my responsibility. I am firmly convinced that this project, when completed and operating, will advance all areas of science and technology. And I mean, seriously, all areas can benefit from this particular facility once it's completed. By the time it's finished, will have spent a full third of my professional career working on this project. And I'll guarantee if I didn't think it would be beneficial, I would not have made that type of commitment. So let's talk a little bit about it. First of all, if you want a Nobel Prize, there's been quite a few Nobel Prizes given out lately based on neutron research. Now, what do these neutrons do? And it's extremely important. They do two things. They show where the atoms are, and they show what the atoms do. To make it very brief, you can study the functionality and structure of materials using this source. Solid materials, liquids, biological, non-biological, it doesn't matter. Pick whatever you want to look at, you can use neutrons. This facility is close to the University of Tennessee, and I'm hoping in the Department of Engineering that some graduate students will do some of their research out there in the future. And remember, point this out, structure determines properties. And right now, 3 forms of carbon, graphite. You can see the structural form of this. It's why it feels sort of smooth and sort of rubs under your fingers when you touch it. Diamonds, extremely hard because of the structure. And then recently, the buckyballs, or the bucky tubes, or whatever you want to call them. Structure is definitely important in materials, and you need to know that structure if you want to know how that material is going to work. If anything on this particular view graph I want you to go away with is I sort of want you to remember that at room temperature, neutrons have a velocity of about 2,200 meters per second, and they have wavelengths that are in the nanometer range, okay? I think everybody in here realizes that neutrons have both particle and wave properties. And another important thing about neutrons is they have a magnetic dipole moment, which can interact with other magnetic fields and tell you information about the structure of those magnetic areas. For example, disk, where you store information on, for example. There'll be some parameters that I'll be talking about. I won't go into too much detail about them. But you hear, this right here represents a relationship between those where they're relating the velocity of the neutron to a temperature, to a wavelength and frequency and so forth. But we won't go into anything in detail because you could spend a week, a semester, or whatever you want to learning about neutron scattering and how you obtain all the data out of it. By neutrons, I will not give examples on all of these today, but I will mention this very briefly, is that neutrons have the right wavelength to study nano-sized particles. You saw that previously because the wavelength of neutrons at room temperature or colder are in the nanometer range. Neutrons measure the velocity of atoms. You can literally watch reactions go with the neutrons from this facility. Neutrons see the nuclei. In other words, you can see a wide range of nuclei with neutrons because the cross-sections are somewhat constant over that range. Neutrons see light atoms next to heavy ones. You cannot do this necessarily with X-rays. You can with neutrons. Neutrons penetrate deeply into matter. Think about one application there is looking at residual strain in systems by using neutrons. And also, as I mentioned earlier in a little more detail, neutrons do have magnetic moments, which you can utilize to study the magnetic character of other materials. Here demonstrates the range in which neutron scattering has been used, complex nuclei, all the way down to quantum corals of iron atoms, or nanotube transistors, or nanotube electronic systems. You can take a look at those systems by utilizing neutrons. And that's why you've probably heard talking about nanoscience lately in the news especially. There is a building being built at Oak Ridge right at the Spallation Neutron source, which will be devoted entirely to nanoscience. So hopefully some of you will be out there someday. So I said neutrons see the nuclei. If you use X-rays, hydrogen, you hardly even see them, and as you go to the higher Z elements, they become more and more dominant. So it'd be very hard to see a hydrogen atom next to some higher Z material. But notice the neutrons. Roughly, the cross-sections are such that you can see a wide range of nuclei within the structure in roughly an equal basis. So neutrons are very important to remember. Nuclei here, hydrogen, you almost forget it using X-rays. One application, as I mentioned earlier, was residual stress, and obviously welding of rivets. Someday, instead of using rivets to put airplanes together, they will be using welding techniques. But usually what happens when you have a system like that, for example, a turbine blade in which you want to attach the turbines to the rotor, you introduce, just by that manufacturing process, internal strains within the system in which you can use neutrons to look. Here, for example, is just an example of one way that the system was welded together, but it's obvious from this that it is unacceptable because the residual strain is too high. Again, a conventional heat treatment. Again, you check it with the neutrons. Again, the residual strain is too much. But finally, you use a new technique, check it, For example, this might be resistive welding, and you look at the system for that, and it turns out that you're within a safe range that you can do it. So you can look at different manufacturing processes to find out what the residual strain is. Neutron C elementary magnets, and obviously if you just think a second, you can see the applications here. Maglev trains, having better systems there, more stable magnets. Credit card strips on the back, everybody knows the application there. Generators, cars in general, and obviously disk storages. Anything that uses magnetics, you can determine about the characteristics of that system using those neutrons. So there's a broad range of research that can be carried out utilizing these room temperature neutrons and colder neutrons. So what do they measure out of these systems? Obviously we generate the neutrons, and I'll give you some more information about that in just a few minutes. But what they basically measure is neutron scattering based on these parameters that I mentioned earlier. The wavelength, the energy, and the vector, which is basically a relationship to the momentum of the neutron. It comes into the sample, it hits there at the detector area, and what they're doing is measuring the intensity as a function of the angle as it builds up. K initial, momentum initial vector, final momentum vector, Q, the difference in the momentum vector. And in this situation, the initial momentum is equal to the final momentum. And basically, you're saying that there's no energy or momentum transfer of the system. Obviously, that's an elastic scattering. But out of that system, they generate and obtain data. And you can see resonances throughout the structure. There's a certain amount of hand-waving and art to this science of reconstructing exactly what that material looks like from this data. And that's why I mentioned earlier, you could spend an entire semester and years of your life learning how to do that. The other is, again, the sample and the detector. Here you have your phase space vectors coming in. They're going out. You're starting to measure intensity. At the same angle, you're measuring a spectrum and the energy change. In this case, as you might expect, it is a reaction in which momentum and energy are not the same as the initial particle coming in. They are different, but you do get a substantial amount of information out of this system, and with a little bit of magic, which I will flip through this fairly fast, you can fold that data into this by Fourier analysis, come out with what you think the structure of the material is. I want to say one thing about this before I go on, is that you probably noticed here that we have coming into the system, quote, monoenergetic neutrons. How do we get those monoenergetic neutrons? I'll show you that in just a little bit. But it's very important. In a reactor source, which has been used, you obviously have a continuous spectrum of neutrons. So how do you get, if you want a specific neutron energy, how do you get it out of a reactor spectrum? You use crystals and let it interact with the crystal. At a given angle, you can select a specific energy. With a spallation neutron source, with a short pulse source, because we know the distance between the source and where the detector is, and the neutrons are produced very quickly, you can use time of flight to get that energy information. And in addition, in contrast to the reactor, you can get a lot more data sampled out of a spallation source short pulse than you do a reactor. I think everybody in this room, since it's nuclear engineering, knows what a reactor spectra looks like. Okay, I'll take that for granted. With a proton going into a heavy nucleus like lead or mercury, which we're using as the target material for the spallation neutron source, you also get out of this more fast neutrons. And when I say fast, I'm talking about greater than 20 MeV out of the reaction of this nucleus. And usually that's referred to as the fast phase of a nuclear reaction. But once that fast phase is over, there's always a certain amount of energy left in that nucleus. Out of that energy, that nucleus can de-excite by, quote, evaporation of additional particles, including neutrons. Obviously, in a high Z, high A material, you're going to get lots of neutrons. And here's something that you probably know or don't know, is that evaporation spectrum to first order is equivalent to that fission spectrum out of U-235 or any other fissionable material. And it's those neutrons that we want at the spallation source to, quote, thermalize and take them to much, much lower energies. So there's where the neutrons come from. This one you're very familiar with. Spallation reactions you may or may not be familiar with. But remember, it's these evaporation neutrons that are the important neutrons in a spallation source. These fast neutrons will go ahead and interact with more nuclei, make more neutrons, etc. As you can see, in a fission, you get about 1 neutron per fission after you have the capture for the fission. In a spallation source, you have about 30 neutrons per proton generated out of it at 1 GeV. Here's a rule of thumb also. A 1 megawatt spallation source is equivalent to roughly a 6 megawatt reactor. So it takes a lot of spallation sources to generate 100 megawatts, for example. But it turns out that the abilities and what you get out of a spallation source much more offsets the number of neutrons that are produced up here in this particular, in a reactor, for example. Okay, let's go ahead now and talk a little bit in general about the spallation source itself. It will be the world's most powerful neutron source once it's finished. The one that's closest to it now is at ISIS in England. They're about 180 kilowatt neutron source. The most powerful short pulse spallation neutron source in the U.S. is the one at Los Alamos at about 70 kilowatts. Then there's one at Argonne National Lab at about 7 kilowatts. This one here will be greater than 1 megawatt with potential of going as high as about 2 to 2.5 megawatts. It's a fairly expensive product, costly facility to build. It's a little over $1.4 billion. We started as a line item project, that is, we could start construction in October of '99. Completion is in June of 2006. As I mentioned, it is a short pulse spallation neutron source utilizing mercury as the target material. And it's being developed by a collaboration of 6 national laboratories plus universities. Berkeley is producing the front end. That has been done, has been shipped to Oak Ridge, has been installed. The warm part of the LINAC is being built by Los Alamos. The cold part of the LINAC, and I'll have a little more to say about that in a second, is being built by Jefferson Lab in Virginia. The high-energy beam transport in the ring area and then the ring transport to the target building is being developed by Brookhaven National Laboratory. The target is being developed at Oak Ridge. The neutron scattering instruments were being developed at Argonne National Laboratory. Now all of our scientists who were there are now down at the site. And also Oak Ridge is doing the conventional facilities. So what does it sort of look like today? And the picture I'm going to show here is in itself a little bit outdated. This thing is moving so fast. You can see now this is the actual construction site, and you can see that it somewhat mimics what you just saw before. Here's the target building, and here is our office complex. So, some of the basic parameters of the source. We'll have a beam power of greater than 1 megawatt, can go as high as possibly 2.5, but that's going to be much later on. The beam energy is 1 GeV, 1,000 MeV. The pulse rate coming into this system is 60 hertz. In other words, it is receiving pulses of protons every 60 seconds. The pulse length is less than a microsecond, and I'm going to come back to this in a second. The energy per pulse, which is hitting the target, is 17 kilojoules per pulse. Now, about 2/3 of that energy stays in the mercury target itself. The rest of it goes out into the surrounding area. We have one target building, and we have 24 neutron scattering instruments that we can put on the system. However, we will have, and this is being furnished by 18 beam lines off of the system itself. Now let me talk about this 1 second, this very short pulse. With today's technology, it's almost impossible to produce a microsecond pulse out of a LINAC. You can out of a rapidly cycling synchrotron, but not out of a LINAC as such. So that's why we have this ring or accumulator ring. Coming out of the LINAC, and I won't tell you all the stuff that goes through it, is basically 1,000 what we call macro pulses. Each one of those pulses is timed such that when it goes into the ring, it will fill about 2/3 of the ring. The time between the pulses is time such that as that first pulse gets back, the second ledge of the next pulse is coming in, and it goes around, and as though first and second come in, the third one comes in, and it is stored basically in a space about this big. So that after basically 1,000 turns, you now have all that 1 millisecond beam stored in the ring. But since I've dumped everything on top of itself, I now have, when I release that beam to the target, I have reduced that millisecond pulse down to a microsecond. And that's how it is done. And you need that shorter pulse such that when the neutrons that you're talking about in the energy range they're in, that pulse is instantaneous to any time scales associated with the neutrons. And all of that happens 60 times a second. As you can tell, within the project, we currently are funding 5 of the instruments. And there was logic behind that, because as technology improves and things change, you want to add instruments later on. We currently only have 6 beam lines left of the 24 that are not asked for today. The rest of these beam lines are being utilized by what is referred to as instrument development team. For example, Lee could come up here and say, hey guys, I've got an idea for a neutron scattering instrument to do this kind of research. Let's go to the SNS and say, I'd like to do it. Write a letter of intent, send it in. If the letter of intent's okay, you'd give a formal presentation. If the SNS said, yeah, that looks good, we'd really like to do that, Lee would go on to the DOE or any NSF or wherever you could get funding, private sector, and say, hey, here's some really good stuff we could do if we can get funded. If he's funded, he comes back, since the SNS has said yes, he builds that detector in collaboration with the SNS. So you have your own detector, which you get roughly 40% of the time on the instrument. The other 60% time is given out to other people on a proposal-graded usage. Okay? So it's possible to do this. So bear that in mind, and we still have some beam lines left if you're interested in one. There is one beam line here, which is referred to as the fundamental physics beam line. They're building a, quote, neutron research laboratory with that beam line. It's not for materials research, it's for pure research. And that beam line is being developed by Jeff Green. And I think is Jeff associated with UT? I want to say yes and no, but I can't remember. Maybe through physics. Yeah, thank you. And so he's working to develop that. And so we have one of the 24 that's literally dedicated to some basic physical research. I also want to mention that Urey and Company are also trying to develop a neutrino detector, which I think is going to be placed, is it in this position? Next to 18. Next to 18, sorry, I've got to go up here, you're right. Sir, it will be situated in this area here. The purpose of that detector is to look for neutrino nucleus interactions, to determine the cross sections for them, which can be used in various cosmological models of the universe to check those models and everything, especially in supernova, et cetera, et cetera. Okay, target systems in the project. Through January of this year, the R&D is 93% complete. The only R&D left is for the instruments. The design is 94, most of that's instruments. The procurements are 95. Construction is 69. We are approaching 3 million hours of safe work. This is this is a milestone, believe me, guys. With that many people on site and that kind of heavy steel work and everything, to get to 3 million hours is really an effort. Total project's about 75% complete and good progress on all technical fronts. So let's look at some few pictures of the site. These were taken some time ago, but they're somewhat more impressive than some of the ones you'll see later on. Everything sort of has dirt back on it and the building is finished. This right here is the target building, because we're sitting probably on the only ridge in East Tennessee that doesn't have bedrock 5 feet below. And it was literally because of the way the glaciers, I think, came through this area many years ago and just pushed the dirt aside, is that bedrock below this target building is about 100 feet down. And since this target building has areas in there where the floor loading is 16,000 pounds per square foot, the building had to be very stable. So there is 1,000 mini piles, micro piles, drilled down to bedrock to stabilize this building. So this building's not going anywhere. If the accelerator moves, they got to find us again because we cannot move this building. It is fixed in space. But this right here is the basement. On the pad, there's the 5 feet of concrete that's there. Here is the front end, and here is the LINAC tunnel before it was filled back in, and this building going in next to it here. This here is the Plystron gallery area where they get the power. You can see here before any of the accelerator components were put in, looking back up the actual LINAC tunnel itself. Finally, here is the ring, the accumulator ring that I spoke of. So the way the thing does is the protons are coming here, they bend at this point, go there, they enter the ring at this point, go around and around that 1,000 times, and finally come out over here and go into the target building located at that point. Now the next picture shows you a little more of what it looks like more today. You can see that the LINAC is now buried. Proton beam from the front end coming down. And you'll notice that if it does not kick out to the ring, it goes straight ahead into the LINAC tune dump, which is a 7.5 kilowatt dump, passive dump. No active cooling at all there. Here's the ring area, the ring service building. Again, it's going around and it's released out to the target building. This right here, if the kicker magnet fails to kick, that proton beam is dumped into the extraction dump, which again is a 7.5 kilowatt dump in itself. There's actually 3 dumps at this facility that we had to build and design. The other one is back on this corner over here called the injection dump. It has to operate. Anytime the facility is operating, that dump operates because remember, we're accelerating negative hydrogen ions. They pass through a thin graphite foil to strip them to hydrogen, H+. Obviously, some of them will miss the foil. Some of them will not be totally ionized. Some of them will go through as neutrals, so they're taken to another foil. Those that pass through like that are then taken to this injection dump, which has a total capability of 200 kilowatts. In essence, if we have to use that amount of stoppage, we're hoping we're only going to have to use about 40. But remember, I told you ISIS, the most powerful spallation neutron source currently in existence, in itself is only 180 kilowatts. So we're throwing away enough energy to make another ISIS over there. Okay, here is the target building. Today, this roof isn't entirely on there. This area right here will be left open so that we can install our equipment down into the area inside the building. Here is inside the building. You're going to hear me talk a little bit later on about a thing called a monolith. It's this part of the target building is the monolith. This here inside will be where the mercury target is. These right here are the neutron ports where the neutrons come out to the various instruments around that area. And if I'm looking at it on the right, the correct side, Urey's neutrino detector is on the other side about where I'm standing. So the RTBT is right here, which is the ring to target transport section. This right here is high density concrete, and generally everything inside that area is steel. So there's about 8,000 tons of material just in the shielding monolith. Outside, remember I said on some instruments you want to do extremely good timing because you want high resolution. This detector here, which is the backscattering spectrometer, is actually located roughly 100 meters outside the target building from the target itself. Again, another detector located outside is the powder diffractometer. All of these instruments do things slightly differently when looking at various types of material. Here is, hopefully, by the end of, this building's pretty well enclosed, but hopefully by the end of July, the target systems will be in that building, the central lab and office building of this year. We're so certain of that, we'll either be in that building or trailers. We've given up the lease on where we currently are in town, so we're out somewhere, so it doesn't matter. All right, a little bit about the accelerator. As I said, the front end up here, we start off with H- into a radio frequency quadrupole, which focuses the ions coming out of here up to an energy of 2.5 MeV. Remember I said that the beam coming there needs to be chopped so we can get those 1,000 macro pulses to get them into the ring. That's done in this area. They enter a drift tube LINAC, a coupled cavity LINAC, and then probably the most unique part of this accelerator, the LINAC, is the cold part. This is the first superconducting LINAC for the RF system. And the reason they've got a medium beta and a high beta, remember beta is basically the velocity of the particle divided by the velocity of light. As the proton is increasing in energy, obviously it changes the time and the structure and everything in the cavities themselves. If you take an electron and kick it, you're already relativistic, so everything can be constant. But as the proton accelerates, you have to change these cavities to tune to that velocity of the proton itself. To give you a very quick example, drift tube LINAC is an old accelerator technology. If you have a cavity in which you have a standing wave, as the wave goes positive, it would accelerate particles one way. As it goes negative, accelerate them the other way, positive, negative. So the charged particles would never accelerate. But if you take that standing wave and inside that standing wave cavity put a metal conductor, and that is as the wave goes this way, it accelerates the particle. Then as the wave tries to go back the other way, let the particle enter that conductive cavity. It will never see that field, so it'll go constant velocity for a little bit until time just right and right fitness. As the wave comes back to drive it again, it's back out into the field again and it accelerates again. So as you can see, it's called a drift tube LINAC. It literally drifts through these tubes until it hits the field again and it's re-accelerated. Obviously, you cannot take it all the way up to the highest energies, otherwise the length of these tubes become excruciatingly big, so you can change the technology to different areas. Again, they have to be, tuned to the velocity of the proton. Okay, let's talk a little bit more detail about what's in the shielding monolith and what we do. The proton beam in this situation is coming in from this side. It's the mercury target located in this area, generates the neutrons, and I'll show you in a minute a little more detail about this area and what's done to those neutrons. But surrounding this mercury target system is basically a liner, which is inside the concrete area, which is basically 10 meters across. It's large, and the predominant material in there is steel. We have some shutter gates. Obviously, as the people are doing their experiments, they don't want to have to shut down the accelerator to change out stuff. So what is done is these shutter gates are moved up and down to close the neutron beam off. And I know somebody in this room who did a lot of calculations on those, sitting in the back of the hall up there by the name of Thomas Miller, to look and see how much shielding you actually need and how much streaming goes around that corner there. And so the shutters are used to shut off the neutrons coming to the sample so the guy can reach down in there, put in another sample, and keep right on going, raise the shutter back up. Here we have a target card assembly, which extends all the way back into the hot cell area, because every once in a while, that target module has to be changed out, which hits, a beam actually hits the front end. There's a couple driving factors to that. One's radiation damage, and the other has to do with something that I'll talk about too. It's cavitation-induced erosion, and I'll get into more detail on that in a little bit. Again, the hot cell is where we do everything remotely, because this mercury becomes so activated, nobody can get in there and do it except remotely. Here is in the hot cell itself. We are in the hot cell here. Here is the mercury pump. Here's the circuit system. Here is where the target card assembly is drawn back into the mercury, into the hot cell. And the disconnects when that occurs is that the mercury in the system is dumped into one of the storage tanks, and the disconnect occurs at this point right here off the card assembly. So you drain the mercury, make the disconnects, pull the thing back with remote manipulator arms and servo manipulator arms inside. You can change out the target module itself and replace it when its lifetime has been reached. Here I've moved in very close inside the shielding monolith to show you, and I've also messed you up because now the protons are coming in from here. As we all know, the protons should come from the other direction. And unfortunately, it's listed this way. Here's the mercury target container. Neutrons are produced in here. They go out into a reflector area. We're utilizing beryllium, backed up by basically steel on the outer side. We have within this system 3 cryogenic moderators utilizing hydrogen. Those are the ones that produce the very cold neutrons. And we have one water moderator, and I've got this backwards. That should be the hydrogen there, and that's the water there. Utilizing water just at room temperature as the moderator system. Obviously, this gives you the room temperature neutrons. This gives you the neutrons at much colder temperature. And you utilize those cold neutrons primarily to look at systems where you need longer wavelength neutrons, molecules, so forth. Here are the disconnects. You can see the bolts that have to be taken off to remove this module when it's back in the hot cell. Here are the utility lines connecting to the service, to the target module, supplying vacuum, helium, and cooling water to the shroud that's located in that area. Obviously, you don't want exactly, if you did not put a safety shroud around this target container, if you had a mercury leak there, it's all going to get dumped in this area, and that is really a major cleanup. So they decided, and we decided initially, to go ahead and put an inflatable shroud, a water-cooled shroud around the target module itself. Okay, things are occurring in Target. We finished our detailed design last year. Our current mode of operation right now is oversight of the fabrication and installation. We are developing detailed installation schedules and plans. The development of the subsystems and integrated tests, which are to occur basically a year from this July, are very important to us because we've got to make sure, since we've got to do all of this servicing remotely, that everything in that hot cell has been checked out and checked out thoroughly. We expect first beam on target in February of 2006, and then operations shortly after we pass, which is referred to as CD4. That's when the DOE says, hey, you stop being a line item project and you're now an operating facility. And it's fairly easy for us to meet CD4. The accelerator delivers 10 to the 13th protons per pulse to the target. And we measure 1/20th of what we anticipate in the number of neutrons per stir radian per proton out one of the neutron beam lines. So we should be able to make CD4 fairly easily and then get on into the fact of working this accelerator one up in power. And we anticipate in about 2 years that we will have an operating facility. Remember, it takes time once an accelerator is even operating to get it to go up to full power and become very efficient. Even though we had confidence in all the technology that we had developed for this facility, we still had some issues associated with what we were doing, and we developed a fairly detailed R&D program around about 5 or 6 topics. First of was steady-state power handling. That is, could we get the heat out of stainless steel utilizing mercury? In other words, what is the thermal weathability characteristic of mercury? Some people say it's really good, some said it was bad. The data was all over everywhere. And so we decided we've got to check that out to be certain. We also, because of the way we had designed our module, the mercury comes in from the front, comes together in the middle, splatters like mad, and then goes back down the center. We had to know in that situation how much of the hot spots and recirculation zones were generated inside that flow loop. Did they flush out? Was the flow constant, stable in that area? So we needed to know that information. Also, we needed to know information on the thermal shock. Remember, I'm delivering to a volume that's about this big, 17 kilowatts per pulse, of which 2/3 of that, or about 11 to 12 kilowatts, stays in that target. And I'm delivering that in a microsecond, less than a microsecond. Now, the temperature rise per pulse is not all that big. It's about 3 degrees C. But if you look at the rate at which that temperature is increasing, it's over 1 million degrees C per second. That in itself is going to generate pressure waves. As a result of those pressure waves, and this we did not originally have in our R&D program, we encountered cavitation-induced erosion, and we were pitting the front surface of that target container so badly that we were afraid that it might last 2 hours, much less the 7 weeks we had anticipated. So we had a big problem there that we found out. We had material issues. We needed to know what are, in an accelerator environment, the characteristics of stainless steel. As many of you might know, stainless steel, unirradiated, has about 60% ductility. As you irradiate it, that ductility goes away and it becomes more brittle, so that by the time you're up around 5 dPa, you're probably down to 5 or 10% ductility. So we needed to know. Stainless is a really forgiving material when you start out, but it embrittles rather rapidly. We also needed to know what is the compatibility of mercury with other materials. Mercury dissolves gold, silver, nickel, lead, chrome, and obviously a couple of those elements I mentioned are in stainless steel that we're using for the container, in particular nickel and chrome. And so we needed to know how much of that might be leached out by being in contact with mercury. We wanted to demonstrate that we could operate a big loop. And we also wanted to demonstrate that we could maintain that loop remotely. So that was a big part of our R&D program. And least but not last, we needed nuclear data. We needed data in the forms of deterministic cross-sections, for example, like Dort or Tort, that we could utilize to do some of these big calculations like Thomas did on the reflectors. And also we needed to have coupling codes that couple Monte Carlo codes in 3D to either 2D or 3D deterministic codes. And so all of that was developed as part of the R&D program for the target. As I mentioned before, the flow is in this direction. Bulk flow in here, and then the bulk is out through the center of the target module. We did not want to rely entirely on the bulk flow to cool the front face. This actual target module has a duplex structure. See these holes here, which actually it starts from the bottom, comes up the bottom, comes across the front face, and then back out the top. We utilize that to take care of the cooling of the front face, and we don't rely on the bulk flow. Now, this is not a crack in the target module, trust me. We've been trying to get that out of there for years, but it keeps coming back. That is not a crack. Okay. Some of the loop parameters, as I mentioned, at 2 megawatts, if you have 2 megawatts on the target, about 2/3 is contained in there. Normal operating pressures are fairly low in this system, 0.3 megapascals. Flow rate, we're pumping enough mercury to fill your gas can in your gas tank in about 6 seconds, 5 to 6 seconds. So we're flowing mercury fairly heavy. There's lots of stored energy in that loop when it goes. Temperature, the inlet temperature, bulk temperature is about 60, outlet temperature is about 90. Total mercury inventory is about 20 metric tons. Pump power is about 30 kilowatts. Now, there are slightly hotter areas in the mercury of about 120, 140 degrees C. The reason we're trying to keep this as low as possible is that we are, at least by inventory, a nuclear facility, Category 2. And everybody knows if you release mercury at very high temperatures, it's very volatile. You get out all the stuff that can get out, gases and stuff, and it's pretty bad. So if you keep it at a low temperature, the amount that might escape is substantially reduced. So we operate at a fairly low temperature. Okay, we built 3 thermal hydraulic loops to check out quite a few things. We built a mercury thermal hydraulic loop to determine wettability, design data for the target window, and also a corrosion erosion test, since mercury can do that, but we found out that, hey, no real problem in any of that. We built a loop, a water thermal hydraulic loop, to check the recirculation zone. In particular, this is just like we had before, water coming here, water coming there. We actually found out from that loop that there was some instabilities the way it was designed, and modifications were made to that loop to minimize that. It was having a tendency to all go to one side rather than bouncing back and forth on the flow. The third loop was our target test facility. This was a full-scale loop. This building here is basically a little bigger than this room here, but not quite as wide. It's a little bit narrower than this room, but as long. But the full facility is as big as the one we will have up on the Chestnut Ridge when the source is completed. We use this for full-scale, as a full-scale loop. We did some of our final computational fluid dynamic analysis on the very front module. And we checked and verified the mercury process equipment that it would work. And we had developed some operational experience. One of the things that we did find out in this loop, and I can't remember the exact fault, the failure mode, was that we had several valves in there. You know, we would cut off, cut on, cut off, cut on. It turned out after we utilized those valves for about 3 weeks, they failed. And what had happened when mercury was able to leak up into one area between the baffles and the valve, and you tried to cut it off, it was like trying to push something against a hydrostatic head. It wouldn't shut down. And so obviously we're not using those valves up on the site. Valves that we've got now will not do that. Okay, so here is our thermal hydraulic analysis. Here's the data that we obtained. We wanted to be on this curve or close to this curve, and so lo and behold, once we got the data out, we knew that wettability was confirmed. We could cool the front face at 2 megawatts by utilizing the mercury and the flow loop that we had laid out across the front face. On our computational fluid dynamics, the flow, as you know, that anything kind of things go around the corner, like right here, and it's going to move out of that area, that things become, you induce in that area recirculation zones. And the thing we wanted to be absolutely certain was that zone did not heat up to the point where we would introduce boiling in that area. We wanted to make sure that area flushed out, and lo and behold, if you watch, you'll see these red balls eventually kick out and go down and become blue balls. So it does flush through the system. I lost my page. I'll use the other method. Okay. One of the things that we wanted to know was the flow rate of the mercury as it comes in the side, goes through the center, and goes back out the center section. And so the only way we could do that was to introduce bubbles into the system so that our ultrasonic device would work. We tried introducing bubbles into the system. It did not work. It did not work at all. And so the only thing that saved us on this is we changed one of the flow sections back there because we thought we had to redesign it so that it was at 90 degrees. And because it was at 90 degrees, we were introducing cavitation in that area. And due to that cavitation, it introduced bubbles. And due to those bubbles, we were able to carry out this experiment. So by accident, we were able to finish that and get that experiment done. But we did confirm that our computational fluid dynamic capabilities were accurate enough that we could continue to design the system without any further work. Here we have the pressure waves and the heating in the mercury itself. I'm going to point out to you there the pulse hit, and you can see the pressure waves propagating through the system. And as I mentioned before, the pressure waves are such intensity that it is possible to introduce cavitation in this system. The cavitation can produce erosion because of the bubble collapse on the surface. It collapses in a fashion like this. If here's the surface and here's the bubble generated in the mercury, it has a tendency to collapse like that. And you literally have a mercury jet, a very small, 10, 50 microns, going right into the surface container, and it does pit. Well, we found out that that was a problem. And you can take a look. This right here is pitting in stainless steel. There was in a test at Los Alamos at the WNR facility in July of 2000. And after 200 pulses, this is the kind of thing we saw. And if you think about it, 200 pulses is 3 seconds of operation. And you can imagine that our front face there was like 150, 1,500 microns thick. And these pits were on the order of 10 to 20 microns. And it doesn't take too much to think this thing's going to eat through in just minutes. And so obviously we had to do something. So we went to the WNR with a heavy campaign of targets, 21 different targets, looking at all sorts of things. Most of the targets rectangular in shape, just like our target is. Many had top and bottom plates because we got this duplex flow across the front face. Stainless steel, cold worked, and we did 100 pulses to look and see at the various things. We looked at power dependence, bold gas layer mitigation. We looked at geometry effects. we looked at material variation, and we looked at the effect of the number of cycles. That is, in this case, we went up in one case to as many as 1,000 cycles. The reason we didn't want to go higher is we start to activate that mercury fairly heavily above 1,000. Is the sound on the system? Maybe we'll do it here. There it goes. That's the sound of the proton being hit the target. Okay. High power. Now here's something I want to show you that's quite important. If you look at the situation, here is an unirradiated target. Here's one that's irradiated. What we did was to look at various parameters as to how to qualify the erosion. We finally ended up utilizing mean depth of erosion as our merit of how to measure and compare the various things. Notice, if we put a bubble layer on the front face as well as we could do, we reduced by 94% the erosion that was on a basic stainless steel 316 material. If we electropolished the surface, we reduced that erosion by 97%. We still didn't think that was enough. If we introduced coasterization on the surface, it was almost nothing, didn't even pit it at all. Coasterization is a quasi-high temperature carbon gas immersion of graphite literally into the surface of the stainless steel. It more or less produces a type of ferritic steel close to the surface that's extremely hard. But notice this one here. This one is very important. If we reduce the power by 1/2, the erosion went down an order of magnitude. There is an extremely strong function, power function, on this erosion. It turns out it's about the energy deposition to the 4th power. So if you go to 2 megawatts, it's a heck of a lot worse than it is at 1, by 2 to the 4th. So you've got about 16 times worse at 2 megawatts as compared to the 1 megawatt case. So we knew that at least we could coasterize the system, and operating at 1 megawatt is not nearly as bad as the 2 megawatt, and we only guaranteed 1. But we think now that we can survive approximately 2 weeks at the 1 megawatt. Now, we could not go to higher pulses because the system would be so activated we couldn't utilize hands-on maintenance to it. We'd have to go remotely. It would cost too much. So we devised offline tests to help us with this system. We had a simple drop test at Oak Ridge. Jerry had a magnetically driven impact test where they now can go up to 60 hertz. And I'll mention this in a second. And a lithotripter test, we tried this one. This is the one to bust the kidney stones. Okay? And then finally, we did an ultrasonic horn for really going way out there and seeing just what kind of characteristics, so we could look at a lot of materials quickly. To make a long story short, this test here, when Jerry did this test at 20 hertz, this is a Japanese test, they found cavitation-induced erosion. When they went to 60 hertz, which we were operating at, it went away. And why does it go away? For the same reason that doctors who want to get to the golf course very quickly cannot, because they have to operate at 1 hertz. If the doctors say, I've got to get out of here, crank that sucker up to 20 hertz, the kidney stones don't break anymore. And the reason is you introduce bubbles into the system, and those bubbles act as a cushion. So right now, we're very happy at 60 hertz at 1 megawatt at Oak Ridge. The Japanese are crying. Their system is to come up at 20 hertz, and they're still seeing it. So they've got a more severe problem than we have. Okay, again, you can see this is the beam test, 2.5 megawatts, a lot of pitting, 1 megawatt, very little. And here's some of the pitting that was seen in the offline test, the ones in the bottom. Here you see as a function of the cycles, and to give you an example, this right here at this point is about 12 hours, half a day. And you'll also notice that after that, for most of the materials that we were interested in, and this is seen in water systems also where you have cavitation erosion, that there is a break-in time before you start off on eroding the material away. And we saw that also. But you'll also notice, if you compare this line here, which is for the 316 cold work stainless steel, and compare this to this line here, which we have more data now, and the line still holds, which should be the coasterized system, you can see a substantial reduction in the cavitation-induced erosion. And you better believe our first target module that goes into this facility will have that coasterization process done to it. We have a person today down in I can't remember the name of the company, it just left me, Bodycoat. At Bodycoat in Alabama, making sure that our target module will be designed such that it can fit in their facility and everything. So right now we think we have, at least for the 1 megawatt case and for up to 2 weeks or so, the cavitation-induced problem solved. But there's large uncertainties, as this view graph shows, and I won't go into detail here into any more detail, to say that we still are continuing our R&D program through collaborations with Jülich in Germany, CERN, which is in Switzerland, and the Japanese, which are located obviously in Japan. So we do have an external program that are still looking at all sorts of high-powered target development, and we're pretty certain right now that we have, at least for our case, the thing under control, but we're looking now how to go to much, much higher powers. Remote handling, again, we have demonstrated in our facility that we can handle remote handling. We have gone through all sorts of processes, taking the target module off, putting it back on, timing those processes, what went wrong, what can we fix. I did have a video on here one time, and the gentleman who put it on there for me, I didn't get a chance to look at it first. And it showed the guy standing there in the manipulator arms and doing all sorts of stuff. Now, he's sort of behind a window over here. And all of a sudden, something jammed, and he just walked around front and shook it loose, walked back, and continued on. And I said, for God's sakes, edit that out. That's not going to work. But anyhow, we were quite comfortable with all the tests we had done. And we also have, later on in the project, starting in, as I mentioned earlier, from June, July of next year through the end of next year, 6 months scheduled to check out all of our remote handling capability. So to conclude, one more view graph, sorry. Materials R&D program, as I mentioned earlier, we did do quite a bit of tests in accelerator beam, for example, at Los Alamos, which is about an 800 MeV proton beam. And we did irradiations up to 4 and 5 dPa in stainless steel samples, both in the proton beam and neutron environment, and then only in a neutron, quote, neutron environment. And we did confirm that 316 is still a good material for our target module. We did some fatigue tests between mercury and air environment in a high cycle regime, and I think these tests were done at the University of Tennessee. I think Art is working on, where'd Art go? I've lost the name. Art's working on the flow characteristics of our mercury target right now, also on that. With the mercury thermal hydraulic loop, we did some, for erosion test, we did some high temperature. Now notice, the higher the temperature, the higher the erosion you should expect. And also, we're operating much lower at less than 100 degrees. Velocity's right. We have completed the 2,000 hours now, that's an error. And we saw no gross effect of erosion due to that speed of the mercury going through the system. Mercury compatibility, we did mercury in contact with stainless steel, no real problem. There is some leaching out on the very small amount on the surface, but it seems to stop after a certain depth. We also did it around aluminum, and we made a mercury vapor and had it in contact with the aluminum, since we are using aluminum as part of our moderators, the moderator containers. And so our materials program basically validated everything that we needed. I want to leave you with one last view graph, and remember, if you want to know where the atoms are and you want to know what their structural characteristics are as well as their functionality, we've got one hell of a source on the hill. So I hope I see some of you up there someday. Lee, thank you.
Excuse me, Ron. We do have time for a question or two. I have a question. You've done a lot of R&D on this target. It's a mercury target, lots of energy being supplied to the target, lots of uncertainties. Looks like you tried to think of everything. As an engineer, we take worst case scenarios, and so let's assume for the moment that this target, for some reason, doesn't work like we want it to work.
I'm glad you asked that question.
Okay. What is our backup in case this target doesn't work like we want it to work? Do we have a backup, and what is it?
We have a backup. Most of the other facilities, ICES, Los Alamos, Argonne, utilize a solid target water cooler. We have developed a backup target that will fit in the same volume, and we have included, you remember that big card assembly that holds the target? We've added additional pipes in there that can carry water to that target for the cooler, just in case. The design is sitting there. All we got to do is do some final work on it, send it out, have it manufactured, and the system will be ready to go. So we have a backup in case all hell fails.
Very good, very good. One final question. Bill?
What is the basis for pulse rate of 60 hertz?
I think it's the line frequency. It turned out that we knew initially that to generate a system that would go less than 60 hertz was going to put a lot of requirements on the front end of the system. We didn't realize what a real requirement it was going to put on the target end, but that was one of the basic reasons. At the time, I mean, like I said, the Japanese are looking at a 20 hertz system. They've got lots of problems. Our system is primarily 60 hertz. Now, we are contemplating a second target building, which we will do 15 to 20 hertz at a lower power. But you can imagine, even lower power, each pulse has about as much energy in it as the high-powered station. But it'll be for super cold neutrons. And the reason you have to go to a lower frequency there is due to the fact of frame overlap. By the time this first neutron is really going slow gets out there, bam, you're hit with a second pulse, and the fast neutrons get out there before your slow neutron do. So you have to literally go to a very low rate to prevent a lot of frame overlap like that.
Okay. I see several new faces in the audience today, and the new people that are here may not know that we do have refreshments downstairs on the second floor, and everyone is invited, and Tony will be available to answer more questions. But before we adjourn for refreshments, let's express our appreciation again to Tony Gabriel for his presentation. Question similar to Lee's. Burns over, you put photons on your target. How will you detect heavy or not heavy?
Well, I can tell you the current.
I suggest that y'all walk down, taking down.